Welcome to this series of supply chain lectures. I'm Johannes Vermorel, and today I will be presenting languages and compilers for supply chain. I do not remember having ever seen compilers discussed in any supply chain textbook, and yet the topic is of primary importance. We have seen in the very first chapter of this series, in the lecture titled Product-Oriented Delivery, that essentially programming is the key to capitalize the time invested by supply chain experts. Without programming, we can't capitalize their time. We treat supply chain experts as expendable, essentially. Furthermore, in this very fourth chapter, through the two previous lectures, mathematical optimization for supply chain and machine learning for supply chain, we have seen that essentially those two fields, optimization and learning, respectively, during the course of the last decade became driven by programming paradigms instead of remaining a set of algorithms and models as it used to be the case in the past. All of those elements point out to, I would say, the primary importance of programming languages, and thus it begs the questions of a programming language, and thus of a compiler, engineered to address supply chain changes. The purpose of this lecture is to demystify the design of such a programming language intended for supply chain purposes. Your company is probably never going to engineer such a programming language of its own. Nevertheless, having some insight in the topic is fundamental in order to be able to assess the adequacy of the tooling that you have, and also to assess the adequacy of the tooling that you intend to acquire in order to address the supply chain changes faced by your company. Furthermore, this lecture should also help you to avoid some of the pretty big mistakes that people who have no insights whatsoever in this topic tend to do in this area. Let's start by dispelling two delusions that have been prevalent in enterprise software circles for the last 3 decades or so. The first is the Lego programming delusion, where programming is thought as something that can be entirely bypassed. Indeed, programming is hard, and thus there are always vendors who will promise that through their product and fantastic technology, that this programming that is so hard can be turned into a visual experience that is accessible to anybody, removing entirely all the difficulty of programming itself. So that the experience essentially becomes akin to just assembling Lego, something that even a child can do. This has been attempted countless times in the last couple of decades, and it has always invariably failed. At the very best, those products that were intended to deliver a visual experience turned into regular programming languages that are not especially easier to master than compared to other programming languages. This is, by the way, anecdotally, the reason why, for example, in the series of Microsoft products, there are the Visual series. There are Visual Basic for application, there is Visual Studio. All those visual products were introduced in the 90s with the hope to turn programming into some kind of purely visual experience with designers where it would be just drag and drop. The reality is that all those tools did ultimately get a very significant degree of success, but they are just fairly regular programming languages nowadays. There are very, very, very little left from the visual parts that was, I would say, at the inception of those products. And so the Lego approach failed because fundamentally the bottleneck is not the hurdle of the programming syntax. This is a hurdle, it is, but it's a very minor one, especially compared to mastering the concepts that are involved whenever you want to roll out any kind of sophisticated automation. Your mind becomes the bottleneck, and your understanding of the sort of concepts that are at play much more than the syntax. The second is the Star Wars tech delusion, which consists of thinking that it's just easy to plug and play fantastic pieces of technology. This approach, by the way, is and this delusion is very appealing to vendors and in-house projects alike. Essentially, it becomes very tempting to say there is this fantastic NoSQL database, we can just drop it in. Or there is this fantastic deep learning stack, we can also take it in. There is this graph database, let's have it in. There is this distributed actor framework, etc., etc., etc. And you see, the problem with that, it's treating technology as, I would say, Star Wars is treating technology. So in Star Wars, when you have a mechanical hand, the hero can just get the mechanical hand, and this is it. It works. But in reality, integration problems dominates. This is the crux of the problem. You see, Star Wars bypass entirely the fact that there will be a whole series of problems. First, you will need probably tons of antibiotics. You will need a very long re-education of the hand so that to be able to use the hand. You would need also a maintenance program for the hand because it's mechanical. And what about the power source, etc., etc. All of those problems are just bypassed. You just plug in the fantastic piece of technology and it works. This is not the case. In reality, integration problems dominates. And for example, in large software companies, most software engineers are not working on fantastically cool pieces of technology. Actually, the bulk of the engineering workforce of the vast majority of those large software vendors is dedicated just to the integration of all the parts. So you need, whenever you have modules, components, apps, you need a small army of engineers to just glue all those things and bring them together. And you have to have all those engineers to cope with all the problems that emerge when you try to bring those things together. And you also, even once you've passed all the hurdles of the integration, you still need a lot of engineering workforce just to cope with the fact that when you modify any part of the system, you tend to create problems in other parts of the system. So you need this engineering workforce to basically chase around to fix all those problems. By the way, also as an anecdote, one other problem that I've witnessed with, I would say, core pieces of tech is the Dunning-Kruger effect that it creates among engineers. You know, you introduce a cool piece of text in your stack, and suddenly engineers, just because they've started to toy with a piece of tech that they barely understand, think that they are suddenly AI experts or something. That's a typical case of Dunning-Kruger effect, and that's very strongly related to the number of cool tech pieces that you just drop into your solution. And thus, in conclusion, you see, with those two delusions, we see that we can't really bypass the problem of programming. We have to address it frontally, including the difficult parts. Now, having said that, the interesting thing about programming languages is that enterprise software vendors keep reinventing, accidentally, programming languages, and they do it all the time. Indeed, in supply chain, there is a ferocious need for configurability. As we have seen in previous lectures, the world of supply chain is super vast. Problems are super numerous and diverse. And thus, what happens is that when you have a supply chain software product, you have an extremely intense need for configurability. Anecdotally, this is why configurations, just configuring a piece of software is typically a multi-month and sometimes a multi-year project. It's because there is a massive amount of complexity that goes into this configuration. And thus, configuration settings have very, very frequently extremely complex. Those configuration settings are not just buttons and checkboxes. You can have triggers, you can have formulas, you can have loops, you can have all sorts of blocks that are going with that. And actually, it very quickly, I would say, goes out of control. And what you get through those configuration settings is an emergent programming language, except that you never really, formalize this configuration as a programming language. It was like an emergent property of the system that is being engineered. And also, because it's an emergent programming language, it tends to be a very crappy programming language. Now, it turned out that engineering an actual programming language is a very well-established engineering task. This is a very, very well-established academic field. But even if you want to go to the practical side of the equation, there are dozens of books about the practicalities of engineering an actual production-grade compiler. So it is, and we will be getting back to, I would say, this historical context in a minute. Now, a compiler is a program that is going to convert instructions, typically textual instruction, into machine code, or at least a lower level form of instructions. Whenever there is a programming language, there is a compiler involved. For example, inside an Excel spreadsheet, you have formulas, and Excel actually has a compiler of its own to compile those formulas and execute them. Thus, most likely, the entire audience has been using compilers for their entire professional life without knowing that they were doing this. So, now on the schema that you can see on the screen, you would see, I would say, a typical pipeline. And this archetype fits pretty much all the programming language that you've probably ever heard of. Python, JavaScript, Java, C#, all those languages have a pipeline that is essentially similar to the one that is outlined here. And in a compiler pipeline, what you have is essentially a series of transformations. And at every stage of the process, you have a representation that represents the entire program. So the way a compiler is engineered is to have a series of well-identified transformations. And at every stage of the process, you're working with the entire program. It's just represented differently. And the idea is that every transformation is responsible for a very well-specified set of problems. So you address those problems, and then you move to the next transformation that will address another set of process. And typically, at every single stage, you go to something that is closer to the machine-level code. Now, the compiler typically starts with the scripts, and it will start with transformations that are very close to the syntax of the programming language of interest. And by the way, during those early transformations, this is where a typical compiler will capture the sort of I would say, syntactic mistake that will even prevent the compiler to turning, I would say, an invalid script, a script that does not even represent a valid program, into something that can be executed. And again, we will be getting back to have a closer look at a compiler pipeline later on in this lecture. Now, this lecture is the 5th lecture of the 4th chapter of this series. In the first chapter, I presented my views about supply chain, both as a field of study and as a practice. In the second chapter, I surveyed the methodologies that are appropriate to deal with the situation as they are found in supply chain. And as we have seen, most supply chain situations are fairly adversarial in nature, and thus those situations tend to defeat naive strategies. We need to have strategies and methodologies that are resilient to adversarial behaviors from all parties, within the company and outside the companies. The third chapter is dedicated to supply chain personnel, and essentially the third chapter is entirely dedicated to the study of the supply chain problems themselves. What is it that we are trying to solve in the first place? And we need to be very careful. So those supply chain personnel are fictitious companies, and the idea is that we need to be very careful not to entangle, when we start to process, to proceed in this field, not to entangle the problem that we are uncovering with the sort of solution that we can imagine to address this problem. Those are two distinct concerns. We need to separate the problem from the solution. The third chapter is entirely dedicated to the problem part of the analysis. And the fourth and present chapter of this series of lectures is dedicated to the auxiliary sciences of supply chain. And those auxiliary sciences are not supply chain per se. Those are sciences that are very, very helpful to the practice of a modern supply chain, but they are separate. They are separated science. Nevertheless, as I illustrated in a previous lecture, just like nowadays, you would be very, very skeptical about a modern physician that would pretend to be, a very good doctor without having ever heard of anything about chemistry. I believe that a modern practice of supply chain requires to be at the very least, familiar with tons of, or at least a fairly extensive series of auxiliary sciences that let you, achieve this modern practice of supply chain. So in this chapter, we are currently moving through the ladder of abstractions. We started this chapter with the very bottom and literally the physics of computing, with treating about the computing hardware. Then with algorithms, we moved into the realm of software, starting to pay attention to the smallest bricks of interest, which are algorithms. Then we introduced mathematical optimization, which is of very high interest for supply chain, but that also happened to be the foundation of machine learning. And today we are introducing languages and compilers, and those are essential to introduce any kind of programming paradigm, or to actually implement any kind of programming paradigm. And while the topic of languages and compilers can come as a surprise to the audience, I believe at this point, for the part of the audience who had the chance to assist to the previous lectures, it should not be too much of a surprise. Indeed, we have seen that mathematical optimization and machine learning should nowadays be approached through programming paradigms. So that really begs the question of how to implement those programming paradigms, and that leads us to the design of a programming language and its supporting compiler, which is exactly the topic for today. This is the summary of the rest of this lecture. We will start with high-level observation about the history and the market of programming languages. We will review industries that represent, I believe, both respectively the future of supply chain and also the past. Then we will gradually delve into the design of programming languages and of the compilers, moving forward with, I would say, lower level concerns and the technicalities that are involved in the design of a compiler. Since the 1950s, thousands of programming languages have been brought to production. Estimates vary, but the number of programming languages that have been used for production purposes is probably ranging between 1,000 and 10,000. Naturally, many of those languages are just variants, cousins from one another. Sometimes it was even just the code base of the compiler that just was forked into a slightly different direction. It is notable that several very large enterprise software expanded quite a lot through precisely the introduction of programming languages of their own making. For example, there is SAP who introduced ABAP in 1983, and Salesforce did introduce Apex in 2006. And even Microsoft started out before Windows engineering the Altair Basic, a third, another programming language, as soon as 1975. So we see that enterprise software companies are no stranger to actually the introduction of programming languages. And actually, there is quite a few of them where those programming languages were maybe not the initial impulse, but they were really instrumental to the enormous growth that made those companies the giants they are nowadays. Historically, those of you in the audience that are old enough to remember the 90s might actually remember that vendors at the time were marketing third generation and fourth generation programming languages. And the reality is that there was identified a whole series of generations, first, second, third, fourth, etc., even leading to the fifth, where essentially the community stopped counting in terms of generation. Indeed, during the first, let's say, 3-4 decades, all those programming languages were following a nice progression toward higher level of abstractions. But by the end of the 90s, there was already many more directions beside having a higher degree of abstraction. So basically, those languages kept being developed very aggressively, except that they were going into many more directions than just a higher level of abstraction. That was depending essentially of the use case. And so the bottom line is that crafting a new programming language has been done many, many times. It's a whole field of engineering, and as I said, there are entire books dedicated to the subject from a very, very practical angle. And I would even go as far as saying that as a practice, the engineering of a new programming language is something that is much more grounded and predictable than, let's say, carrying a data science experiment. There is a near certainty that you will get the result that you want if you're doing the adequate engineering, considering what is known today and what is already, readily available as knowledge. It's a very specialized knowledge, but it's a very, very well-established one. And all of that really begs the question: what about a programming language specifically engineered for supply chain purposes? And indeed, there can be significant upside in terms of productivity, reliability, and even supply chain performance. In order to address this question, I believe we need to have a look at the future. Fortunately for us, the simplest way to look at the future is just to have a look at one industry that has been pretty much consistently 1 decade ahead of everybody else for the last 3 decades or so. And this industry is the video gaming industry. This is a very, very large industry nowadays. Just to give you a sort of scale, the video game industry is now 2/3 of the aerospace industry worldwide, in terms of comparative size. And the video game industry is growing much, much faster than aerospace. So a decade from now, video games might actually be bigger than aerospace. Now, the interesting thing about those video games is that this industry has now a very, very well-established structure. And let's have a look at it. First, we have game engines. The two leaders are company named Unity and Unreal. And those game engines, they features essentially the low-level components that are of interest to do super intensive, refined 3D graphics, and also they are laying out the landscape for the low-level infrastructure of your code. And so there are a tiny few companies that engineer very complex products called game engines. And those game engines are pretty much used by the entire industry. And now we have game studios. And game studios, for every single game, they will develop the game code. The game code is going to be a code base that is typically specific to the one game being developed. So it has its own engineering team. And if the game engine requires very, I would say, hardcore software engineers that are very, very good technically, but that don't necessarily know much about gaming, the development of game code is not as, I would say, intensive in terms of pure raw technical skills. However, the software engineers who are developing the game code need to understand the game and that they're working on. And the idea is that the game code is going to be the platforms that establish all the sort of game mechanics. But the catch is that when the game code is developed, it doesn't specify the fine prints. This is not a task that is, I would say, managed by software engineers. It is typically done at the stage of the game rules. And the game rules are actually implemented by game designers. Those game designers, they are not software engineers, and yet they write code. But they write code in the sort of scripting languages that are being made available to them by the engineering team that is dealing with the game code. And so we see that we have those three stages: game engines, super technical, hardcore software engineers. They are like core building blocks. Then we have studios. They have engineering teams, one typically per game, and they develop the game as a platform for game mechanics. And then finally we have the game designers, and who are not software engineers. They're really game specialists, and they implement the sort of behavior that will make the gamers, the clients at the end of the pipeline, happy. And the interesting thing is that nowadays, the sort of the game code are like mini platform for gaming are even very frequently made accessible to the fan base. And so it means that game designer can actually write rules and potentially modify the game, but actually fans that are just regular consumer of the games can do that as well. And there is even some very interesting anecdote in this industry. For example, the game Dota, which is incredibly Dota 2, which is incredibly successful. Well, the first version of the game that was just named Dota, it was just a modification of an existing game. It was a pure fan-based modification of the game World of Warcraft 3. So you see, this degree of configurability, this degree of programmability that you get at the level of game rules is very, very extensive, because it was possible from a game, an existing commercial game, World of Warcraft 3, to actually create an entirely new game, which then became a massive commercial success of its own through the second version. So now, this is interesting, and we can start thinking by looking at the gaming industry, what does it mean for the supply chain industry? Well, we could think about what sort of parallel we could draw. Well, in terms of, we could think that we could have a supply chain engine that is taking care of the very, very difficult algorithmic parts, the low-level infrastructure, the core technological building blocks that would be sort of things about mathematical optimization and machine learning. And the idea is that per supply chain, for every single company, you would need an engineering team to actually bring all the relevant data, and because there is an entire applicative landscape, so you need to glue all of that. And then, as a third stage, you will need to have the equivalent of the game designers that would be supply chain specialists, who are not software engineers, but they are the people who will actually write full code, but simplified code, all the sort of rules and mechanics that are needed to actually implement the sort of predictive optimization of interest for the supply chain. So you see that, and I believe that the gaming industry gave us a very vivid example of what is likely to happen in the supply chain space in the decade that is coming. Now, so far, the gaming industry approach in supply chain remains science fiction, except for a tiny few companies. And shameless plug, I believe that most of those companies happen to be clients of Lokad. But back to the subject of today, we have seen in the previous lecture that Excel remained the #1 programming language that is in place in this industry. And by the way, in terms of programming language, Excel is actually a functional reactive programming language. So it's even its own class. There is even its own class of language that are similar to Excel. And you might be hearing nowadays from vendors that are proposing to upgrade supply chains using some kind of data science setup. However, my casual observation over the last decades is that those initiatives, the vast majority of them, have just failed. And so this is literally already the past. And in order to understand why, we need to start looking at the sort of list of programming languages that are involved. If we are looking at what is on the left, we see that Excel only involved essentially 2 programming languages. We have the Excel formulas, and we have VBA. And VBA is not even a requirement. You can, with just VLOOKUPs, you can go super far with Excel. So typically, it's going to be just one programming language, and a programming language that is accessible to non-software engineers. Now, what you have on the right is the list of programming languages that is required to replicate the capabilities of Excel with some kind of data science setup. And we see that this is a list where we have actually quite a few elements. We will need SQL, and potentially several dialects of SQL to access the data. So those are programming languages. We will need Python to basically implement a sort of core logic that we need. However, Python on its own tends to be dramatically slow, so you might need like a sub-language, which is like NumPy. And then at this point, you are still not doing anything in terms of machine learning or in terms of mathematical optimization. So you see in terms of true hardcore numerical analysis, so you will need something else for that. And that's, again, a programming language of its own, and it's going to be, let's say, PyTorch, for example. Now that you have all those elements, well, you have quite a few moving parts already. So your configuration of the application itself that you're building is going to be quite complex. So you will need to have a configuration. And this configuration is going to be written with yet another programming language. It's going to be JSON or XML. So arguably, those are not super complex programming languages. True, but it's more to add to the plate. And then what happens when you have so many moving parts is that you typically need a build system and something that can just execute all those all the sort of compilers and all the sort of mundane recipes that are needed to produce the software, and that's going to be your build system. And build system have typically languages of its own. The traditional approach is a language called Make, but there are many others, many contenders. And then, well, Excel is able to display the results. It's not just pure logic. So you need to have a way to display things to the user, to the human user, and also to visualize stuff. And all of that is going to be done with a mix of JavaScript, HTML, and CSS, and that's a series of extra additional languages. And so you see at this point, this is like a long list, and I'm just simplifying. An actual production setup can actually be more complex than that. And thus, this explains why most companies that try to go for this, I would say, data science pipeline, that have tried to go for this data science pipeline during the last decades have overwhelmingly failed. It's, and thus they have just stayed with Excel in practice. The reason is that it involves mastering almost a dozen programming languages instead of just the one of Excel that we mentioned for the case on the left. And at this point, we haven't even started to touch any of the actual supply chain problems. We have just been discussing the sort of technicalities that were in the way to actually start doing anything. Now, at this point, let's start thinking about what a programming language for supply chain would look like. And first, we have to decide what is inside the language and what belongs to the language as a first-class citizen, and what belongs to libraries. Indeed, with programming languages, it is always possible to essentially offload capabilities to libraries. For example, let's have a look at the C programming language. It's considered a fairly low-level programming language. C does not have a garbage collector. However, it is completely feasible, there are even open source projects for that, to use a third-party garbage collector as a library and thus to leverage garbage collection inside a C program. However, due to the fact that garbage collection is not a first-class citizen in the C programming language, the syntax tends to be relatively verbose and tedious. Now, for supply chain purposes, there are concerns like mathematical optimization and machine learning that are usually treated as libraries. So we have a programming language, and all those concerns are essentially offloaded to third-party libraries. But however, if we were to engineer a programming language for supply chain, then it would really make sense to have those concerns being engineered as essentially first-class citizen in the programming language itself. Also, it would also make sense to have relational data being part of the language as a first-class citizen. Indeed, in supply chain, the applicative landscape, which includes many pieces of enterprise software, has relational data, as in relational databases, SQL databases, all over the place. Indeed, pretty much, I would say all the enterprise software products that exist nowadays have at their core a relational database, which means that for supply chain purposes, as soon as we will want to touch the data, the reality is that we will interact with data that is relational in nature. The data presents itself as a list of tables that are extracted from all those databases that are powering all those apps, and every table has essentially a list of columns or fields inside. So that's I would say our relational data environment that is going to be 99.9% of the data that we need to process. So that really makes sense to have that within the language. And then what about the UI, the user interface, and the UX, the user experience? One of the super strong point of Excel is that all of that is completely embedded into the language. So you don't have a programming language and then all sorts of third-party libraries to deal with presentation, rendering, user interaction, etc. All of that is part of the language. So that having all of that being made a first-class citizen would also be of very relevant interest as far as supply chain is concerned, at the very least, if we want to be able to be as good as Excel can be for supply chains. Now, in language design, the grammar represents the formal representation of the rules that defines a valid program according to your newly introduced programming language. Essentially, you start with a piece of text, and first you will apply a lexer. So a lexer is a specific class of algorithms, or you can even think of it as a small program. And essentially, the lexer decomposes your piece of text, the program that you've just written, into a sequence of tokens. And typically, the lexer isolates all the variables, all the sort of symbols that are at play in your programming language. And the idea is that the grammar, it helps converting this sequence of tokens into the actual semantic of the program. The semantic will define what is it that your program that you've just written, what does it mean? What are the sort of exact non-ambiguous set of operations that needs to be made so that we can execute this program. So, and the grammar itself is, as an object, typically approached as a trade-off between the concern that you want to internalize inside your language and the sort of concept that you want to externalize. For example, if we approach relational data as an external concern, so that the programming language that is of interest, just treat that as something that is outside the programming language. That means that the programmer, in order to interact with relational data, will probably need to introduce a lot of specialized data structures like dictionaries, lookups, hash tables, etc., to perform manually inside the programming language all those operations. If the grammar wants to internalize the relational algebra, it means that the programmer can typically write all the logic or the relational logic directly in its relational form. But that means that suddenly all those relational constraints and all this relational algebra becomes part of the burden that the grammar has to carry. Now, from a supply chain perspective, we see that as relational data is super prevalent in enterprise software, it makes really a lot of sense to have a grammar taking care of all the relational concerns directly at the grammar level in the language. Now, grammars in, I would say, in computer science are an enormously studied subject. This is absolutely not new. They have been around for decades. And yet, it's probably the single area where enterprise software vendors fails the hardest. Indeed, when they invariably end up conjuring accidental programming language that, I recall, just emerge naturally whenever you have complex configuration settings at play and that you want to have conditions, triggers, loops, responses, and all of that, you typically need to take care of this language instead of letting it just emerge of its own. And what happens is that when you don't have a grammar, whenever you bring changes to the application, the application that has all this configuration, then you end up with very haphazard, consequences on the actual behavior of the system. And by the way, this also explains why upgrading from one version of a piece of enterprise software toward another piece is usually very complex, because the configuration is supposed to be the same, but when you actually try to run the same configuration into the next version of the software, you get completely different results. And again, if we kind of go back to the root cause, where it turned out that there is no grammar, so there is no established formalized semantic about what the configuration is going to mean, and that's pretty much the root cause of all those problems. Now, the typical way to represent a grammar is formally the Backus-No form, BNF in short. And this is a kind of a special notation. This may seem very technical, but it's not actually very that technical. On the screen, what you can see is a mini programming language that represents US postal addresses. Each line that has an equal sign represents what is called a production rule. So what you have on the left is a non-terminal symbol, and what you have on the right of the equal sign, is a sequence of terminal and non-terminal symbols. The terminal symbols are in red, and they represent symbols that cannot be derived any further. That's why they're called terminal. And then the non-terminal are all those symbols that are within brackets that can be derived further. And by the way, this grammar here is not complete. There would be many more production rules to add to have a complete grammar. I just wanted to keep this slide reasonably concise. And so a grammar is actually something very straightforward to just define what is acceptable in terms of syntax for your programming language. It also ensures that it will be non-ambiguous. Now, it's not because it's written with the Backus-No form that it's going to be a valid grammar or even a good grammar. No. If we want to have a good grammar, we need to do a little more than that. And actually, the mathematical way to characterize what is a good grammar, and I will get back to what do I mean by good grammar in a minute. So if we want to have a good grammar, is to have a context-free grammar. So a grammar is said to be context-free if the production rules can be applied for any non-terminal irrespective of the symbols that you find on the right and on the left. Thus, the idea is that a context-free grammar is something where you can apply essentially the production rules in any order, and as soon as you see a match, a derivation, you just apply it. Now, what do you get out of a context-free grammar? Well, what you get is a grammar that, if you change something in your grammar, and this something actually creates an ambiguity, well, it will the compiler will not be able to compile anymore the program where the ambiguity happened. And this is something that is of primary interest whenever you intend to maintain, let's say, a configuration for a long period of time. And in supply chains, most I would say pieces of enterprise software are very, very long-lived. It is not infrequent at all to see pieces of enterprise software that are, I would say, that will keep operating for 2 or 3 decades. And at Lokad, we are serving over 100 plus companies nowadays. It is fairly frequent that we are extracting data from systems that have been in place for over 3 decades, especially with large companies. Thus, if we go back to the context-free grammar, what you get with a context-free grammar is essentially the guarantee that if there is change to be brought to this language, and remember when I say language, I can mean something as basic as configuration settings, that you will be able to identify the sort of ambiguities that emerge when you apply this change, instead of just having those ambiguities just happening without even you realizing that you have this problem, and thus having all those problems when you want to upgrade from one system to another. Now, what happens when people don't know anything about grammars is that they manually write a parser. This is, if you've never heard about a grammar, what a software engineer would do, he would write a parser, so just a program that just haphazardly creates a sort of tree that represents, the parsed version of your program. And the problem with that is that you end up with something that is incredibly, you end up with a semantic for your program that is incredibly specific of the version of the program that you have. So again, if you change this program, you change the semantic, and that you will get different results, which means that you can have same configuration but different, behavior for your supply chain. Fortunately, in 2004, there was a small breakthrough introduced by Brian Ford with a paper titled "Parsing Expression Grammars: A Recognition-Based Syntactic Foundation." And essentially, with this work, what Brian Ford did provide to the community is a way to basically formalize, to bring a late formalization to the sort of accidental ad hoc parser that exists in the field. For example, those grammars are called, PEG, and with PEGs, you can, convert those kind of semi-accidental, semi-empirical parsers into actual formal grammars of some kind. By the way, this is what you get with, for example, Python. Python doesn't have exactly a context-free grammar. Python has a PEG, and PEG is kind of fine if you have an extensive set of automated tests, because in this case you can deal with, I would say, the preservation of the semantic over time. Indeed, with PEG, you have a formalization of your grammar, so you're actually in a way better, in a situation that is actually better compared to not having any grammar and have just a parser. However, in terms of evolution of the semantic, with a PEG, you will not automatically detect that you have a change of semantic if you change the grammar itself. Thus, you need to have, on top of your PEG, you need to have an extensive suite of automated tests, which, by the way, is exactly what the Python community have. They have a very robust and very, very extensive set of automated tests. Now, from a supply chain perspective, I believe that not only, obviously grammars are of interest, if only to realize that you need this, but I believe that it constitutes those grammars a litmus test. You can actually test enterprise software vendors. When you're discussing with a vendor and that you see that you're discussing with a piece of software that has a significant complexity, you should be asking the vendor, by the way, I see that this configuration is fairly complex. What sort of grammar do you have? And if the vendor is answer with what's a grammar, then you know that you're in a lot of trouble and that maintenance is going to be hell, and at the very least, it's going to be very slow and very expensive. Now, programming is very difficult, and people will get tons of things wrong. There is no workaround, unfortunately. If it was easy, we would not even need programming in the first place. A good programming language minimizes the time it takes to identify an error and fix it. This is one of the most critical aspects of a programming language in order to ensure a decent productivity for whoever happens to be writing code in this programming language. Now, let's consider the following situation. As you write code, if the error can be detected as you type, just with a red underline, just like a typo in Microsoft Word, if you can detect the error in real time as a typo with a red underline, then it means that you can probably, the feedback loop to fix the error can be something as short as 10 seconds, which is very, very tight and really what we're looking for. If the error can only be detected when you start running the program, then, well, the feedback loop is going to be something like at least 10 minutes long. Indeed, in supply chain, we will very frequently have a large data set to crunch. We will have all the historical data to process. Thus, we can't expect, the program to just start going through all this data in a matter of seconds. As a result, if the problem only happens what is called at runtime, what the program is executing, the feedback loop will be something like 10 minutes or more, as a rule of thumb. Now, if the error can only be detected after the script completes, so that means that you can run the program, but the program has an error, but it doesn't fail. So the program completes, it looks fine, except when you do a careful inspection of all the KPIs that you've crafted yourself to basically instrument, what is happening inside your logic, you realize that there is an error. If it's the way you can detect that you have an error, that means that it will take something like 10 hours or more in terms of feedback loop to go to the error whenever there is one. You see, so that we went from 10 seconds, real-time feedback, 10 minutes if we have to run the program, 10 hours if we actually have to inspect the sort of results, numerical results and KPIs produced by the program. And there is worse. If by any chance the sort of program that you've written or the sort of platform on which you operate is not strictly deterministic, so that means that with the same input and with the same data, it can give you different results, which is not as strange as it may sound, because remember that this is supply chain, so we might have things like Monte Carlo simulation going on. So if there is any kind of randomness in the results, that it means that we can have something that fails only once in a while, and thus in this sort of situation, the feedback loop is going to be typically larger than 10 days. So you see, we went from 10 seconds to 10 days. There are massive stakes in tightening this feedback loop. Now, static analysis represents all the set of techniques that can be applied to detect problems, errors, failures, without even running the program in the first place. You see, with static analysis, the idea is that you will not even run the program, which means that you can actually report the error in real time while people are typing just with those red underline, as you're used to, I would say, for typos with Microsoft Words. And more generally, there is a vivid interest to basically try to transform every single problem, and so that it can move up the ladder into an earlier class of feedback, so that you can transform problems that would take days to identify into something that takes minutes, or something that takes minutes into something that takes seconds, etc. And from a supply chain perspective, we have seen in one of those previous lectures that as far as supply chain are concerned, we can expect quite a lot of chaos. This is supply chain. We can't have a super, I would say, classical release cycles where you have where you can wait till the next version of your software is delivered. Sometimes there is just something completely extraordinary that happens, a tariff that changes, a container ship that gets stuck into a canal, a pandemic, whatever. There will be emergency situation, and those emergency situation calls for emergency corrections. And thus, the amount of static analysis that you can do over your programming language pretty much define how much chaos you will get in production, just due to mistakes that have not been captured, in real time while you were typing the code, and where you just, let the script go into production because you had no choice. You had to have a super fast response time because the logic is already broken due to this extraordinary event. Extraordinary event, but in practice it keeps happening. So it's just this event that is extraordinary. There is nothing extraordinary about having surprises in supply chain. This is like bread and butter. Now, there are mathematical proof that it's not possible to detect all errors. As a matter of fact, with a general programming language in a general situation, it is not even possible to prove, for example, that the program is going to complete, which means that it's not even possible that what you've written, if you hit run, will actually not just keep running until the end of time, or more realistically until you decide that something is wrong and you just kill the program. Now, what you get with static analysis is typically 3 blocks. With static analysis, you will be able to sell some pieces in the code are provably good, some pieces in the code are provably bad, and for a lot of things in the middle, well, you just don't know. And the idea is that I would say, the more you displace from don't know to bad code, so basically, the more effort, I would say, in terms of language design, the more effort you will need to convince the compiler that your program is valid. So you see, the idea is that here we have to strike a balance between how much effort do you want to have to basically convince that this programming language is correct by adding a lot of maybe scaffolding to convince the compiler that it is correct, versus how much guarantees you will want to have on the program, again, at compile time, even before the program actually run. So this is a matter of productivity. Now, a quick list that you can see on the screen are the sort of typical errors that are detected nowadays with static analysis. You will have syntax error if you've forgotten, commas or parentheses, for example. By the way, some languages are not even able to outline. Some programming languages are not even able to outline, error, such syntax error before the runtime. This is the case, for example, for Bash, the shell language on Linux. Now, you will outline type errors if you have the incorrect type or incorrect number of arguments for a function that you're calling. You will have also unreachable code, which means that is code that is just fine, except that your entire program can run, and this piece of code will probably never run, so that it's like dead code, or you just forgot to plug something in terms of logic. Then you can also have inconsequential code. Inconsequential code is just code that will actually execute, except that it doesn't have any impact on anything that your script ultimately does in terms of outputs. Thus, it's completely inconsequential. It runs, but no impact. Right? It's a variant of the unreachable code. And then you have the overspending code. This is code that would just run, except that the amount of computing resources that you would need vastly exceed what you're ready to afford for your program. You see, a program consumes computing resources, memory, storage, CPU, and if you can, through static analysis, prove that basically you have a block of code that consumes way more, let's say, CPU that you can afford, considering that you have, let's say, a time frame, you want the calculation to complete under 1 hour, for example, then you would want this thing to fail at compile time. You don't want to run your program for 1 hour, and then after 1 hour, the program tells you, well, timeout, and then fail. That will just, I would say, lead to very, very low productivity if you do it that way. However, there is a twist in practice when it comes to static analysis. It's that as you type, you're dealing all the time with a program that is invalid. Indeed, as you are typing, keystroke by keystroke, you are transforming what is at some point a valid program into an invalid one. Indeed, you are presently typing, and thus, for those situations, I would say, industry-grade solution nowadays is called a language server protocol. So a language server protocol is actually a class of tooling that comes with a programming language. It's fundamentally, it is basically the state of the art when it comes to real-time error feedback on the sort of program that you type. And it's through a language server protocol that you can have all the niceties, such as essentially go to definition when you click on a variable or this sort of things. And by the way, the language server protocol is fundamentally stateful. So it will have a state of its own, and it will remember the last version of your program that was correct, and it will remember the sort of annotations and semantic that was available at the time for this program when it was compiling, so that you preserve all those annotations and extra tidbits when you are dealing with your broken program just because you've pressed an extra keystroke and it's not a valid program anymore. Again, it's really the sort of things that are a game changer in terms of productivity, and whenever there is any degree of urgency, it will make a big difference from a supply chain purposes. Now, let's dig into the type system. As a first rough approximation, a type system is a set of rules that leverage some categorization that exists within the sort of objects within your program, or the sort of categorization of the elements that you manipulate, and that clarifies whether the sort of interaction that are allowed or disallowed. For example, typical types include string, integer, floating point number. All of those are very Booleans. All of that are very basic types. And for example, it will define that adding two integers together is valid, but adding one string and one integer is not valid, except in JavaScript, because in JavaScript the semantic is kind of insane. But type system in general are an open research problem. However, and it can get incredibly abstract. However, to shed some light, we need to clarify that there are two kinds of types, and those two are very, very frequently confused. We have the type of values, and it's something that only exists at runtime when the program is actually running. For example, in Python, if we are considering a function that returns the first element of an array of integers, then the type of the value returned by this function is going to be an integer too. The first element of an array of integer is an integer. Now, from this perspective, all programming languages have types. Though they are all typed. Now, there is the second type, which is the type of variables. That is something that only exists at compile time, while the program is being compiled, and it's not running yet. And the challenge with the type of variables is to be able to extract as much information as possible about those variables at compile time. If we go back to the previous example, if we have this function that is able to return the first element of an array in Python, well, it turns out that assuming that this function is called in multiple places within a Python program, it may or may not be possible to identify what is the type of the return value returned by this function. Because actually, in Python, it's not entirely strong typed at compile time. Now, from a supply chain perspective, we are looking for a type system that really supports what we intend to do for the benefits of a supply chain. And we want to basically be as restrictive as possible so that we can capture problems and bugs as early as possible. But we also want to be as flexible as possible to allow all the operations that could be of interest. For example, let's consider the addition of a date and an integer. In a regular programming language, you would probably say, no, it's not legitimate. But from a supply chain perspective, if we say, well, I have a date, I want to say plus 7 days, I would like to be able to write this date plus 7. And indeed, there are so many operations in terms of planning in supply chain that goes through, that shift dates by a certain number of dates, that it would make a lot of sense to have an algebra where it's okay to basically do an addition between date and a number. Now, is it in terms of type, do we want to allow to add one date plus a date? Probably not. However, do we want to allow the subtraction between two dates? Well, why not? I mean, if we say one date minus another date that happened to be before, then we get the deltas, again, for example, by convention, expressed in days. This thing, again, makes a lot of sense for sort of calculation that would involve with, let's say, planning. Now, types, just still continuing on this sort of dates, there are also other characteristics that could be of interest if we start thinking about what a type system should be doing for us as far as supply chain is concerned. If we still discuss this date use case, then for example, what about restricting the sort of acceptable time range? You see, for example, we could say that dates outside the scope that gets 20 years in the past and 20 years into the futures are just not valid. And chances are that if we are doing a planning operation and at some point in the program we manipulate a date that is more than 20 years into the future, that the odds are overwhelming that it's just a bug. It's not, you're not doing your planning supply chain wise for something that is going to happen, at least in normal industries, for something maybe not in nuclear industry, but in other industries you would not plan, operations thinking at the daily level more than 20 years ahead. So you see, we can not only take the usual types, but redefine them in ways that are more restrictive and more appropriate to what we want to do in terms of supply chains. Also, there is this whole uncertainty things. We have seen in the previous lecture that in supply chain, we are always looking ahead, but unfortunately, the future is always uncertain. So there is always this uncertainty that we need to embrace. And well, the mathematical way to embrace uncertainty is random variables. So we have, a variable that is qualified as random. So it can take a value. It will take a value in the future that will be observed, but it cannot be known for sure right now. Well, it would make sense to have, in terms of types, to have those random variables into the language. That would be very helpful to represent, uncertain future demand, uncertain future lead times, uncertain customer returns, etc., etc., etc. Now, at Lokad, we have engineered Envision, a programming language dedicated to the predictive optimization of supply chains. Envision is a mix of SQL, Python, mathematical optimization, machine learning, and big data capabilities. All of that wrapped as first-class citizens within the language itself. This language comes with a web-based integrated development environment, which means that you can actually write a script from the web, and you have all the sort of niceties that comes with I would say, modern code edition. And those scripts, they operate over, in terms of data-wise, they operate over an integrated distributed file system that comes with the Lokad environment, so that in a way the sort of data layer is fully integrated into the programming language. And today we are, and also maybe as a last point, the script itself is executes on a fleet of machines. So when you run an Envision script, it's not something that runs on one machine, like let's say a Python script. It's fundamentally something that is designed to take advantage of an entire cloud. So when the script is run, it will spread over many machines in order to run faster. And on the screen, you can see the compiler pipeline used by Envision. And today, we are not going to discuss this programming language. We are just going to discuss its compiler pipeline, because that's the topic of interest, for today's lecture. So first, we start with a piece of text. The piece of text is essentially what contains the Envision script. It represents the sort of program that has been written by a supply chain expert, not a software engineer, supply chain expert to actually address supply chain challenge of some kind. That can be to decide what do you want to produce, what do you want to replenish, what do you want to move, or if you want to move, a price up or down. That would be the sort of use cases that we have. So this piece of text contains the scripts. And the idea is that we are going to pass this script and obtain the LST, the lossless syntax tree. The LST is of interest because it's a very specific representation that do not discard any single character. So if you've written a program, when you go into the LST representation, not even the non-significant white spaces are discarded. We preserve every single character that has been typed. Why do we do that? Well, the reason is that if we want to apply any kind of automated rewrite to the program, we need to make sure that the automated rewrite is not balking the existing code. You see, for those of you who have maybe used some tools in the past, there was this situation where if you've written a piece of code and then you let a tool do an operation over your code, and then suddenly all your code is shuffled, the indentation are moved, and thus you barely recognize your code afterward. The way to basically avoid that is to use an LST so that you preserve every single character and you can apply a very local change for only what you need. And what sort of change are you interested in? Well, a super basic, for example, refactoring operation would be, I just want to rename this variable, and I want in the program all the occurrences of this variable to be renamed, but I don't want anything else to be touched. Now, the LST, when we go from the LST to the AST, we simplify the tree. So the AST stands for abstract syntax tree, and we simplify the tree. For example, the parentheses are not needed anymore when we are at the stage of the AST, because when we have like a tree structure, fundamentally it removes the need to have parentheses. We have the priorities of all the operations that are defined through the tree itself. And also we will perform a whole series of called desugaring the tree. So it's a very technical term. In compilation, a sugar is just something, a syntax that is provided for, I would say, for the benefit of the end programmer. So for example, in Python, if you write x plus equal 1, it is a syntactic sugar. It is strictly equivalent to x equal x plus 1, but it's just more concise. And so, and essentially, the plus equal syntax is just a sugar. And there is a stage where, in the compiler, where we remove all those sugars. And this is at Lokad happening between the LST and the AST dominantly. Then moving on, from the AST to the ASG, we essentially flatten the tree. Indeed, think of it, you're writing a program, and some of your statement, you can have fairly big expression. Just imagine, just like in an Excel spreadsheet, you can have a big formula with plenty of terms. And the idea is that when we flatten the tree, we use a very, very well-known technique called static single assignment, if there are compilation experts in the audience. And essentially, what we decompose is that we can decompose very complex statement, where there is a big, highly nested expression, into a sequence of essentially elementary statements. So if I write, for example, A equal B plus C plus D, I have an assignment with one expression that includes two addition, B plus C plus D. And now, if I want to essentially flatten that, I would turn this one statement into two statements, each statement having only one addition. That is exactly what is happening between the transition from the AST to the ASG. Now, from the ASG to the OG. So OG stands for optimization graph. What we do here is we do all the type shaping and all the broadcasting, especially everything that is relevant to this relational algebra. As I said, as I hinted many times before, it turned out that Envision embeds a relational algebra, as in relational database, SQL database, as a first-class citizen. So there are tons of relational operation, and we check that those relational operations are valid according to the schema of the tables we are operating with when we transition from ASG to OG. And OG is essentially the last step of our compiler frontend. And it represents pure elementary relational operations that happens in your program that represent tiny bits of logic, but all of those elements of logic are, like in SQL, they are relational in nature. And the optimization graph is called optimization because actually there are plenty of transformation that happens from OG to OG. So it's not like we go to OG and then we stop there. No, we are going to have plenty of transformation, and actually the optimization graph is precisely engineered to have all those inner transformation. And the reason why we have those transformation is that when you're dealing with relational algebra, it turned out that depending on the way you organize your operation, you can have your program operating much faster. For example, if you just think SQL, if you have a filter, and then you do an operation, or you have the operation first and then you have the filter, it's much better to first filter your data and then apply the operation. Because if, for example, your operation is just touching a few lines in a table that is 1 billion lines long, then you're much better off first applying the filter and then doing the operation on the results, as opposed to do the operation on the unfiltered table and then filter. So that all of those elements happen at this stage of the OG in Lokad. Then, so this was the last step of the front end of our compiler. And now we have the high intermediate representation. The idea is that the high intermediate representation is a very, I would say, clean and stable documented frontier between the back end of the front end of the compiler and the back end of our compiler pipeline. Indeed, unlike the optimization graph, the OG, that is kind of changing all the time because there is tons of heuristics, so it's something that is always kind of under flux in terms of software engineering at Lokad. The high intermediate representation is very stable, and also, so it's a solid, consistent input that can be used by the backend of our compiler, but also it is serializable. So serializable means that this thing can easily be transformed in a pack of bytes in order to just be moved from one machine to another. And this is a very essential property if you want to be able to distribute your calculation. At some point, you need to serialize some aspect of your program and just move it to various machines. So at Lokad, this is at the high intermediate representation that this thing is happening. Now, we go from high intermediate representation to funcs. Funcs are values that are yet to be evaluated. So they represent the atomic block of calculation that happen within a distributed execution. The idea is that, for example, let's say that you want to add 2 gigantic vectors. So let's say you have 2 vectors from a table, and the table has several billions of lines. So this is a very, very big table, and you have 2 vectors that are themselves very, very big. Well, it turned out that there will be a series of funcs that represent various pages of those 2 vectors, and each func is going to individually be responsible for adding a portion of the 2 vectors. And the idea is that a func is something that is only executed on one machine. However, big calculations are split into many, many funcs in order to be able to spread the workload over multiple CPUs, but also over multiple machines if the calculation is sufficiently large to warrant this degree of distribution. Functs are essentially what it's called lazy. So they are not evaluated at first. They are evaluated when we need them, because many calculations can happen before some functs are actually computed. And the idea is that once a func is computed, the func itself is replaced by its results. Now, inside the func, you will find the low intermediate representation. The low intermediate representation represents imperative low-level logic that is run within the func, and it can, for example, include loops and dictionary accesses. And finally, this low-level intermediate representation is compiled to bytecode. So the bytecode represents the end game target of our compiler pipeline. And we happen at Lokad to be targeting the .NET bytecode that is technically known as MSCL. The .NET virtual machine is interesting because it represents a superset of modern CPUs, and in particular, you have directly access to the sort of super scalar instruction, the SIMD, instruction that were discussed in the very first lecture of this chapter. Now, from a supply chain perspective, what is really interesting is that through this arguably complex compiler pipeline, we are reproducing the degree of integration that is found in Microsoft Excel. The language is integrated with the data layer. The language is integrated also with its UI and UX layer, so what you need to see and interact with the outputs of the program, just the way you can see an Excel spreadsheet and interact with it. But unlike Excel, we are going into, I would say, much more interesting territories as far as supply chain is concerned, because we are embracing, obviously, as I discussed, relational concepts as first-class citizen, but also, and I've not really discussed those parts, the mathematical optimization and machine learning concepts. And by the way, both mathematical optimization and machine learning in this pipeline are basically going through the entire pipeline. So this is not about calling a library that sits somewhere. No, it goes through the entire pipeline, and having machine learning as a first-class citizen in your pipeline that goes from the very beginning to the very end, and that is present, along the entire chain, along the entire pipeline, is very important if you want to have error messages that don't happen to be completely opaque. You see, the problem is that when you have a machine learning library, is that if something goes wrong in terms of user experience, or whoever is programming the high-level scripts, this person will be faced with a very, very opaque error message. However, if it's a first-class citizen of the pipeline, that means that you can actually have a feedback loop that brings a very intelligible message that helps this person to actually fix the tidbits of machine learning logic that needs to be fixed. This one is really making a big difference in terms of productivity of your supply chain experts. And as a final topic, a compiler nowadays is almost always targeting a virtual machine. A compiler targets a virtual machine, but this virtual machine, in turn, is compiled toward another virtual machine. And some people have theorized that at the bottom of the stack, there must be a CPU or some kind of computing hardware. But my own personal theory is that it's just a cascade of virtual machines all the way down. Well, more seriously, on the screen, the typical VM layers that are found in a server-based setup. So this stack is very similar to what we have with an Envision script. I've just presented the compiler pipeline. But fundamentally, it would be pretty much the same stack if we were thinking about a Python script, or an Excel spreadsheet that would be operated from a server. When you design a compiler, you essentially choose the layer at which you're going to inject the code. And the deeper the layer, the more technicalities you have to address. And thus, in order to choose which layer, to choose the layer, there are a series of questions that needs to be, or concerns that needs to be addressed. And first is we have security. How do you protect your memory and what the program should or should not access? If you have a generic programming language, then you don't have much options. You will need to operate at the operating system, the guest operating system level, and even that might not be very secure. There are ways to sandbox, but it's very, very tricky. So you might even have to go lower than that. And then the second concern is the amount of low-level features you're interested in. For example, that could be important if you want to achieve a more performant execution in terms of reducing the amount of computing resources that you need to complete your program. And for example, if you can decide to go sufficiently low so that you manage the memory and you manage the threads, and this is good. However, with responsibility, but however, with this power comes the responsibility of actually managing the memory and managing the threads. And then, as a third concern, there are the convenience features, like, for example, garbage collection, having a stack trace, having a debugger, having a profiler. Typically, all the instrumentation that is around the compiler is more complex than the compiler itself. So this is something that is not to be underestimated, the amount of convenience features that you benefit. And then, as a fourth big concern, you have all the resource allocation concern. If you are operating with an Excel spreadsheet on your desk, well, Excel can consume all the computing resources that there is in your workstation. You know, it can take all the memory that you have, all the CPUs, all the disks, etc. There is no question. Your entire machine is pretty much, you know, can get potentially dedicated to your one Excel spreadsheet that you're working on. Now, if you go with Envision or just SQL, suddenly this is not the case anymore. You have multiple users to serve, and thus you have to decide how to allocate the resources. And furthermore, actually, if you go with Envision, it's not just multiple users to serve, it's actually multiple companies to serve, and we have to allocate the resources across multiple companies. Indeed, Lokad is multi-tenant, and it makes sense in supply chain because the need in terms of computational resource and compute resources are very, very intermittent. For most supply chains, you only need a very intense burst of compute for something like half an hour or maybe 1 hour, and then nothing for the next 23 hours, and then rinse and repeat. This is typically scheduled on a daily basis. And thus, if you were to decide to just allocate hardware computing resources to one company, then those computing resources would remain unused 90% of the time or even more. So this is not good. So you want to be able to spread the workload over many machines, but over many companies, potentially companies that operate over various time zones. Now, that's the first and the last concern. And finally, the last concern will be the ecosystem. The idea is that when you decide a specific layer and a specific VM that you target for your compiler, it means that it will be very, I would say, fairly convenient to integrate and interface your compiler with whatever is also targeting the exact same virtual machines. And that brings, the question of the ecosystem. What is it that you can find at the same level than what you target to, not reinvent the wheel for every single tidbits that are involved in your whole stack. So this is the last and important concern. In conclusion, congratulations for the happy few that made it so far. In this series of supply chain lectures, this is probably one of the most technical lectures so far. Compilers are arguably very technical beasts. However, the reality of modern supply chain is that everything gets mediated through a programming language no matter what. There is no such thing anymore as a raw, directly observable supply chain. The only way to observe a supply chain is through the mediation of the electronic records that are produced by all the pieces of enterprise software that are lying around, that are constituting, the applicative landscape. And thus, a programming language is needed. And by default, this programming language happens to be Excel nowadays. However, if we want to do better than Excel, we need to think hard about what does better even mean from a supply chain perspective. And what does it even mean in terms of programming language? Yet, if the company doesn't have the right strategy or the right culture, then no technology will save it. However, if strategy and culture are just sound, then tooling really matters. Tooling, and when I say tooling, I mean potentially programming languages, will define your capacity to execute. It will define the productivity that you can expect from your supply chain experts, and it will define what sort of performance you will get out of your supply chain when you are turning this macro strategy into the thousands of super mundane daily decisions that your supply chain need to make. And that's and so being able to assess the adequacy of the tools, including of the programming languages, is that you intend to use to address those supply chain challenges is of primary importance. If you're not able to assess, then it's just complete cargo cult. The next lecture will be about software engineering. Today we did discuss the tooling. However, the next time we will discuss the people who use the tools and what sort of teamwork is required to do the job well. The lecture will happen the same day of the week. It will be a Wednesday, and it will be 3 p.m. time of Paris. And now I will have a look at the question. Okay, we have a first question from Pankaj Nanani. When selecting software for supply chains, how can enterprises which are not tech-savvy evaluate if the compiler and programming is appropriate for their need? Well, I'm pretty sure that a company, a typical company that operates a typical supply chain is not, I would say, does not have the qualification to engineer a vehicle. And yet, they manage, to purchase trucks that are adequate to their supply chain requirement and transportation requirements. So it's not because you're not an expert and you're not able yourself to rebuild and re-engineer a trucks that you can't have a very solid opinion on whether this is a good truck for your transportation needs. And so here, I would say, again, I'm not saying that those companies that are not tech-savvy should do some kind of an incredible, I would say, to do some leap forward and becomes, suddenly experts in the design of compilers. However, I believe that, in just 1 hour and a half, we did cover quite a lot of grounds, probably with a bit, I would say, 10 hours of of more detailed and slower paced, introduction, you would need everything that you ever need to know in terms of language design for supply chain purposes. So again, this is about, there is a difference between being an expert and just being so incredibly ignorant that people can sell you a scooter pretending it is a truck. That's if we were to translate this sort of ignorance that I observed in terms of design of enterprise software to the automotive industry, people would just claim that a scooter is a semi and vice versa and get away with it. So again, we have to be reasonable about our expectations. As I said, this series of lectures is about auxiliary sciences. So it's not, there is no intent for people who want first and foremost to be supply chain practitioners to be experts in those domains. Nevertheless, by having some kind of entry-level knowledge, you can go very, very far in assessing. And again, the idea is that most of the time, you only need to have just enough knowledge so that you can ask the tough question. And then you will see that if the vendor suddenly end up giving you a completely nonsensical answer, it doesn't look good. Normally, if you're really in command of your subject, you should be able to give a sensical answer to a fairly technical question. But if you don't even know which sort of technical question you should ask, for example, what sort of grammar do you use to support your very extensive configuration settings that you have sitting in the middle of your piece of software, then you can be fooled. So that would be my suggestion is you don't need to become incredibly tech savvy. You just need to become savvy enough so that you're kind of an entry-level amateur that is just enough so that you can poke the holes and assess whether the whole thing falls apart because it was just a show, or if there is an actual substance behind it. And the same is true for mathematical optimization, machine learning, CPUs, and whatnot. It's just the idea is in this series, in this chapter, all the auxiliary sciences, is to know enough so that you can do the difference between something that is essentially fraud and something that is legitimate. And again, I said, why does it matter? We should have honest vendors. Well, for honest vendors, we go back to the second chapter with adversarial market research, and you will see that, I wish we had, that it was all honest, but this is just not the case. So we just need to be prepared. A question from Julia Smith. Did you directly address this issue with the existing programming language not designed for supply chain? This is a very, very good question. Engineering a brand new programming language seems like maybe completely nuts. Why not just say, well, we're just going to go for let's say something that is already well established, like Python, and just bring in the small modification that we need. It would have been an option. The problem is, you see, the main problem is not really what we need to add to those languages, but what we need to remove. My main concern with Python is not that it doesn't do, let's say, that it's not that it doesn't have, let's say, a probabilistic algebra, or it's not that it doesn't have a relational algebra built in. This is not my number one criticism. My number one criticism is that it is a fully capable generic programming language, and thus it exposes the person who is going to write code to all sorts of concepts like object-oriented programming, for example, for Python, that are completely inconsequential as far as supply chain is concerned. So you see, the problem was not so much as take a language and add something, but take a language and try to remove tons of things. However, the problem is that as soon as you remove stuff from an existing programming language, you break everything. And also, for example, I believe that the first release of Python was something like 1990. So this is something like a 30 years old programming language. The amount of code that you have in a popular stack like Python is absolutely gigantic. And for good reason. I'm not criticizing. This is a very solid stack. But this is also an absolutely enormous stack. So in the end, if you want to have something that is, so in the end, we assess our various options, take a programming language, subtract tons of things until we are satisfied with what we have. Consider that there is tons also, all those programming languages, they have tons of legacy of their own, or we did assess how much effort it was to create a brand new language, and in the end, well, it was very much in favor of just creating a brand new language. And remember what I just said in this lecture, engineering a new programming language is a super established field. So although it may sound like something incredible, it is not. You have hundreds of books that gives you recipes. It is now even accessible to computer science students. I mean, there are even professors in computer science department that give an assignment to their students in one semester to actually create a compiler for a new programming language. I know I had one of those professors. So, and it doesn't require, superhuman intelligence. Again, this is a very established field. This has been done thousands of times. So in the end, we decided that supply chains were massive enough to warrant a dedicated effort. Yes, you can always recycle stuff that were not designed for supply chains, but supply chains are, I would say, worldwide, it's an absolutely massive industry and massive set of problems. So we thought, well, considering the scale that we're looking at, it makes sense to do the right thing and do something directly for supply chain, as opposed to kind of do some kind of, I would say, accidental recycling. Another question from Pankaj Nanani. For supply chain optimization, Envision is appropriate as it comprise SQL, Python, etc. However, for WMS, ERP, where process flow is key rather than mathematical optimization, how can you evaluate its compiler and programming language? That is a very good question. Indeed, I mean, by the way, I have been personally toying with the idea. It turned out that there are actors in this industry that did actually engineer programming languages of their own just for the benefits of implementing something that is completely transactional in nature, workflow oriented. So you see, supply chain, the way I see it, it's essentially about predictive optimization. However, Mr. Nanani is completely correct. You have what about all the management part, ERP, WMS, etc. It turned out that there are many companies in this field who have actually crafted their own programming language. I mentioned SAP. SAP has ABAP that is done just for that. Unfortunately, ABAP is kind of, I would say, it didn't age very well. That's my taste. There are plenty of things in ABAP that don't really make sense in the 20th century. You can really see that this thing was designed in '83 and it shows. But for example, in Microsoft Dynamics, the ERP has a programming language of its own. Dynamics AX has its own programming language. And there are many ERP projects that, to a large extent, bring their own programming language. So it does exist. Now, are those languages really the pinnacle of what we can do in terms of modern state-of-the-art programming language in 2021? I don't think so. And that's also the problem that I was saying, that enterprise software vendors keep reinventing programming language, but usually they do a very crappy job at that. This is just very haphazard, engineering design. They don't even take the time to read the many books that I've said that are available on the market. They just kind of do it, and then there are poor engineers that are stuck with a hot pile of mess. So back to your question, I've been even toying with Lokad, venturing in this area and creating a language that was designed not for the optimization but supporting the workflow. But at this point, we're just the growth of Lokad is so much that we can't, we don't have the resource to fork off and deal with the workflows. But I I am absolutely certain that this is spot on, and there will be, new actors that will emerge and that will do a very good job for the management part of the problem. Lokad is only tackling the optimization part of supply chains. There is also all the management parts. A question from Mark Richmond. Python is currently seen as a standard programming language. Are there any ongoing evolutions on the market? That is a very, very good question. You see, when people tell me the standard, well, I've been around long enough so that I've seen, standards come and go. I'm not very, very old, but when I was in high school, essentially the absolute standard was C++. Obviously, in the 90s, C++. This is the standard. Why would you do it any other way? And then came Java. Java around year 2000 and Java plus XML. The combo Java plus XML, that was the standard. Why would you do it any other way? That was the standard. People even said that universities at the time had turned into Java schools. That was literally the term of the day around year 2K. People were saying this is not a computer science university anymore. This is just a Java school. Okay, and now when I founded Lokad a few years down the road, R, the programming language, was all rage. So it was like if you wanted to do anything that was relevant to statistics, Python was still if you go in 2007, 2008, that was still very, very marginal. R was absolutely dominating the fields in terms of statistical analysis. Now, as we progress, in terms of programming languages, essentially C++ faded away. Microsoft did introduce C# in 2002 and the .NET platform that did cannibalize a major part of, I would say, of the C++ ecosystem, because actually a big part of the C++ developers were worldwide, a significant fraction were at Microsoft. Microsoft was already a very, very large, very massive company. And now, so the point that I'm getting at is that it has been a complete ongoing evolution, and that at every single year, people were looking at this as if, there was this standard, but this standard changed all the time. JavaScript had been around for 20 years, but it was nothing. And then there was a book published, I think in 2012. I mean, people can correct me, maybe it was 2009, I forget, called JavaScript, The Good Parts. There was like JavaScript, The Good Parts. It was a book that was something like 50 pages long. And it was just next to JavaScript, The Complete Reference, that was like 800,000 pages. So the good parts were just like super, super thin. And then people realized when there was this book published, JavaScript, The Good Part, that actually JavaScript was not completely insane. You could be using JavaScript for a real project and not lose your sanity in your process. You just have to stick with the good parts. They are very thin. And thus, suddenly, JavaScript was all rage, and everybody converged to JavaScript, and you could see that there were plenty of people that were claiming that JavaScript would take over everything. People started to use JavaScript server-side with a system called Node.js. And you see, every single year, and by the way, Python only rose to prominence a few years back. It has only been something like 4 to 5 years that Python really rose to prominence. Basically, the Python community underwent a gruesome upgrade from the 2.7 version to the 3.x version. And this upgrade took almost a decade, and at the end of this upgrade, when things started to settle down, then Python, the amount of interest for Python was really renewed. But now, if you look at Python, I would say there are many dangers that looms ahead. There are plenty of things that are threatening, to just supersede Python. Python is not a very good language. I mean, not by the standard of 2021. This is a 30-year-old language, and it shows its age. If you want to have something that is almost better in every other dimension except maturity, you could look at Julia, for example. Julia for data science is pretty much superior in every single way to Python except maturity, where Julia is still, I would say, years behind the sort of maturity that you have in Python. So, yes, there are tons of ongoing evolutions. And I would say that it's very easy to mistake the state of the industry for something that is a standard that is supposed to last. For example, again, if you go into the Apple ecosystem, there was Objective-C. It was like a big thing. And then Apple decided to introduce Swift as a replacement. And now Swift is literally killing Objective-C, et cetera, et cetera. So it's really something that is still very much evolving. And my take is that although it is, it takes time. It takes, I would say, the sort of time frame we are talking about is probably 3 to 5 years. But if we look at the ecosystem 10 years ahead, I'm pretty sure that there will be enormous amount of evolution. And I suspect that Python will not emerge as the dominant programming language, just because there are so many things that are rivaling Python and that are actually bringing better answers than Python. Swift, for example, is a better answer for practically all the problems to Python, except some specific data science problems, et cetera, et cetera, et cetera. So there are, depending on sort of problem that you're looking at, there are many rivals and a lot of rivalry, and there are better options, and new, even better options keeps emerging every year or so. A question from Alexei Tikhonov. Food companies and e-commerce startups often think they can win the battle with their data science teams and general purpose languages. What would be your top selling point to make them rethink this approach and make them realize they need something more problem specific? So as I said, this is the problem with this Dunning-Kruger effects that I was referring about. You give a software engineer a mixed integer linear programming system to do essentially integer programming, and the week afterward, this person will think they have suddenly become an expert into discrete optimization. That's Dunning-Kruger effect for you. So what sort of how do I win the battle? Well, truth to be told, usually we don't win them. It just what I do is that I just describe the way the catastrophes will unfold. So what will happen is that it's very easy when you just go with these generic blocks of technologies to do your proof of concepts. So you will have fantastic prototypes. And guess what? Why do we have a fantastic prototypes? Well, this is a Star Wars delusion for you, because as long as you're doing a prototype, you don't have to care about the integration problems. You just take the things piecewise. Thus, your prototypes and proof of concepts and all of that, small scale attempts will just work brilliantly. Again, Star Wars delusions. You have just your piece of technology in isolation. And what will happen is that as those companies are going to start trying to bring those things to production, they will struggle. They will struggle a lot. And most of the time, it will be because of very, very mundane problems. It will not be like grand open problems about the stability of the convergence of a deep learning network or this sort of super difficult problem. No, it will be just super, super dumb problems such as Heisenberg's. It crashed this tonight. I'm rerunning the exact same thing today. The crash doesn't happen. And then, so we say, oh, problem is gone. And then I wait 3 days, and the crash happened again. And I try to reproduce again the problem. I rerun, and the crash doesn't happen. Heisenberg's. The closer you get, the more fuzzy it becomes. Also called quantum bugs. So you see, what I predict to those companies is that they will end up facing ongoing integration issues. They are not like Google or Microsoft or Amazon. They cannot afford to have, if we're talking of startups or e-commerce, they cannot afford to have 1,000 engineers to deal with all the plumbing around. You see, because the thing is that, if we look at TensorFlow is very difficult to integrate. And yes, it's a great product. And at Google, there is no question that that Google has the 1,000 engineers it takes to glue TensorFlow into all their data pipeline and application for their purpose. But the question is, can you afford to have that many people to take care of all the plumbing? And usually the answer is no. And people imagine by just picking those tools that they will just be able to do, again, Star Wars delusion, to just cherry pick things and then put it together and magic, it works. But it doesn't. It requires a massive amount of engineering. And by the way, software, enterprise software vendors, some of them are suffering from the exact same problem. They have way too many components in their solution, and that explains why even deploying a solution, no customization whatsoever, already takes months because there is so many shaky, parts in the system that are only loosely integrated. It becomes very, very difficult. Excellent. I guess this was the last question. Well, I guess see you next time.